Okay, I have started recording. We have 26th of February. We have Maths for Economists. If I'm not mistaken, it's lecture 7, but maybe I'm wrong. Maybe. I hope so. Friday. We continue with linear programming. Okay, let's go on. Just a small off-topic message. This week I have encountered a good source on mathematics for strong students. I have encountered Evan Chen. Yeah. I have encountered a good open book. Evan Chen, Infinite. MFE. It's a funny project of a guy who studies at Harvard, if I'm not mistaken, and he tries to collect everything about university mathematics in one funny document, and that's a very crazy project, and I have encountered it this week, and I like it very much. So if you are interested in math, and obviously that's not for just for preparing for external exams, but if you like to go deeper in other fields, then that may be fun. Okay, you can Google it, and it's available for free. So, okay, linear programming. So off topic is finished. Linear programming. Okay, last week we have discussed that you have two problems that are called dual problems. And today we will use this duality to solve a problem with a lot of variables and a small number of constraints. We will transform it into a problem with a smaller number of variables, but bigger number of constraints. And as we can solve this problem, when we have a small number of variables, then whoops, we have an advantage that we can use a graphical approach. In that case, these, it seems at first glance that it's impossible to use a graphical approach. So first, I would like to introduce this duality a little bit formally. So I will have a standard maximization problem, and I will have a standard minimization problem. In standard maximization problem, I have x that is x1 xn, let's say transposed a column vector. In a standard minimization problem, I will have a vector y, y1, yk transposed, so the number of variables will be different in these two problems, or may be different. And in maximization problem, I will maximize, I will try to maximize C transposed times X in minimization problem, I will minimize y transpose times b, subject to, so here I will choose x, here I will choose y, and I will have some constraints. In standard maximization problem, I will have the constraints a times x is less or equal than b. In minimization problem, I will have the constraint y transpose times a is greater or equal than c transposed. And I have non-negativity constraints. X is greater than 0, y is greater than 0. And these two problems, last week, we have proven, so what we have proven last week? We have proven that first order conditions are exactly the same for these two problems. So we have proven theorem. First order conditions are exactly the same. We have proven that on the example, but if you just replace particular numbers with arbitrary numbers, then you will get a general proof. So basically the idea is the same. You just replace special numbers we have used by parameters, and you have done the honest proof. First order conditions are exactly the same for both problems. And that allows us to go from standard minimization problem to standard maximization problem, and from standard maximization to standard minimization. And let's try to do so in an example. And the idea behind this link, idea behind duality, that x Lagrange multipliers for minimization problem, and y1, y2, yk are Lagrange multipliers for maximization problem. So basically, when you introduce Lagrange function to the minimization problem, and you just call your Lagrange multipliers by x, and you introduce Lagrange function for maximization problem, and you name Lagrange multipliers by y1, y2, yk, then bingo, you have exactly the same first order conditions. Equation in equation, inequality in inequality, exactly the same conditions. Okay, now let's pick up an example, and let's solve this example using duality. And once again, I should mention that you can avoid listening to the lectures. You can just go and read some chapters from Thomas Ferguson. He has a very great style of writing books. They are very clear, linear programming. It's called linear programming, concise introduction. Concise introduction. So maybe that would be a better idea to completely remove lectures and to just answer your questions about what is not clear, but we are not ready for that style of teaching yet. So I will continue my lectures, but no secret will be, there will be no secrets for those who have studied this book. Okay, let's start with example. I will maximize, let me write, I will maximize, I will have four variables. I will have four variables. Wow. I will have, okay, I will start with constraints. X1 is greater than 0, X2 is greater than 0, X3 is greater than 0, X4 is greater than 0. I will have four variables, and we will solve it. I have four variables here. What else should I write? I will have something like 5, something like 2x1 plus 1x2 plus 1x3 plus 5x4 will be less than 7. 1x1 plus 2x2 plus 1x3 plus 6x4 will be, I think, less than 8. And I'd like to have a maximization of what I would like to maximize 10x1 plus 10x2 plus plus 7x3 plus 100, I think. Yeah, I think that would be just a moment. Okay, let's go like that, plus 100x4. I know that is too easy. That is too easy. That is too easy. That is too easy. No, I will write it minimization. And here I have, yeah, I will have like that. Yeah, I like it. Now let's solve this problem. I see that I have four variables. I understand that I'm too lazy to write these first order conditions with Lagrangian function. I'm too lazy because four variables plus 2 lambdas. So imagine that I'm honest and I solve without graphical sketch four variables plus 2 lambdas, 6 variables in total. I'm scared. I'm too lazy. So I will not do like that. I see that that is a minimization problem in standard form, and I will create a dual problem. So I will use graphical approach, but I will go to dual problem. So first step 1, I will go to dual problem. Consider dual problem. Instead of minimization, I will have maximization problem. So how do we calculate dual problem? So first, instead of minimization, we will have maximization. Once again, what is the correspondence? So let me look at the formal definition. We have solved, we have discovered this correspondence last week, but probably you have forgotten almost everything from the last week. So let me draw your attention. What are the weights? Right-hand side will go to the weights, and vice versa. Weights are in the right-hand side. I replace maximization by minimization. I replace inequality in one direction into reverse direction, and basically that's all. Let me do that. I will consider maximization of, first I look at the right-hand side. Right-hand side is 7 and 8. So I will consider maximization of 7z1 plus 8z2. So now I have two variables. And that's much better because with two variables I can draw. Okay, now we move on to subject 2 part. All variables are non-negative. Z1 is greater than 0, Z2 is greater than 0. Now I will create the system of inequalities. I have 4 variables in the original problem, so I will have 4 inequalities in the dual problem. So let's read every inequality. So how to read first inequality? We take basically first column and read it as inequality. So let us look at the first column, 10, 2, and 1. So Z1 will be Lagrange multiplier for the first inequality. Z2 will be Lagrange multiplier for the second inequality. And basically the first inequality will be 2Z1 plus 1Z2 is less than 10. Okay, any questions here?
No, it's okay.
So let's write the second inequality. The second inequality, I read the second column. I read the second column. 1z1 plus 2z2 is less than 10. Now I read the third column. 1z1 plus 1z2 is less than 7. And finally, I read the last column. 5z1 plus 6z2 is less than 100, as far as I remember. And this is a dual problem. And I can easily solve it. Why I can easily solve it? Because I have two variables. I can draw with two variables. The miracle. Any questions about how to go from linear programming problem to its dual?
No.
So basically, if you are if you have some doubts, then just follow this definition of dual problems. If you have standard maximization, the dual is standard minimization. So maybe if your problem is not in standard form, for example, you have maximization, but inequalities are not like that, then go to standard maximization problem and then go to dual. Or maybe your problem is minimization problem, but inequalities are not like that. So first standardize your minimization problem and then go to dual. So maybe we will consider an example how to standardize, but for the moment, let us continue because our problem was standardized from the beginning. So we have found the dual problem, and then we will found the okay, let's solve it. Do I have enough place? Yeah, I have enough space. Yeah, I have enough space. I will just draw everything. This is my Z1, this is my Z2. And I basically draw, I have first, second, fourth inequality. Okay, first one is I have 5 there, 10 here, 10 here, 5 there. Okay, the first one is like that. So that's the first line. The second line is like this. That is the second line. The next line, I need to be a little bit careful where 7 is located. 7 is a little bit closer to 5. Yeah, 7 is closer to 5 than to 10. So be careful, because how many intersections do you have on that or this line? It's important. So in my case, I'm sure that 7 is closer to 5 than to 10. And basically, I'm pretty sure that my line will go like this. Yeah, that's important where intersections are located. If you have a mistake on your sketch, so proportions maybe are not important. Lines may be a little bit curved, but if intersection of line 1 and line 3 is before intersection of line 1 and line 2, then it should be clearly visible on your sketch. So we should understand that our graph is wrong. Our line has thickness, so it's not exactly straight line. So our plot is not.
Boris Borisovich,
yeah.
I'm sorry. I believe that the third line crossing should be above the first intersection of two other lines.
Okay, so let's.
No, I just draw like
Okay,
precisely.
Let's check. That's a good idea. Let's check. Let's check. So this point is. So that's a good idea to check. Yeah, maybe you're right. Maybe I'm wrong. Let's check. Okay, intersection of first and second line. 2Z1 plus 1Z2 is 10. 1Z1 plus 2Z2 is 10. So intersection is Z1 is 3 and 1 over 3. And Z2 is 3 and 1 over 3. So this is 3, 1 over 3. And let's check the intersection of first and third line. Yeah. If I take the first and the third one, 2Z1 plus 1Z2 is 10, and Z1 plus Z2 is 7. Yeah. Okay, that means Z1 is 3 and Z2 is 4. Okay, let me find this intersection. Z1 is 1 and 3, Z 1 and 3. Yeah, you're right. Yeah, that's great. Yeah, you're right. Thank you. That's a great point. 1 and 2, 1 and 3 is that one is, yeah, you're right. That's a wrong picture. Yeah, that's a good reminder that we should be very careful that when we draw our sketch, if you are not sure, it's better to find explicitly the intersection points. Yeah, thank you very much.
Sorry to ruin your graph.
Oh, that's okay. Thank you. Okay, once again, this is line, this is Z1, this is Z2, that is line 1. That is line 2. That is line 3. Yeah, and indeed, this is 3. This is 4. This is 5. 10. This is 7. Okay, and this is 3 with small 1/3. Okay, and the last line is very easy. I'm sure that the last one is very far from the beginning. Yeah, it's something like, it's very far. The line number 4 is like that. And that is line number 4. Now I draw my region. Where is the region allowed is located. I see that my optimization region is here. Okay.
Yes, it's okay.
Okay.
How do I know that I should paint this figure? For each line, I check whether I should paint below it or above it. For this line, the point 0, 0 satisfies the inequality, and the point 100, 100 does not satisfy the inequality, so I should paint below this line. For this line, I should paint below. I check using test point. I choose 0, 0 as a test point, and I just check that 0, 0 satisfies all the equation. So basically, I should paint the region where 0, 0 is located. Okay, now I can solve my, so it was maximization. Now it's maximization problem. So let me draw the level curves of, I draw the level curves of 7z1 plus 8z2 is equal to constant. So these level curves are straight lines, and the slope of these lines, the slope is equal to -7/8. Yeah. So basically, the slope is roughly -1, a little bit less by absolute value than -1. And hence, I conclude that if I draw these lines, so they will go like that. the slope is a little bit less than -1 by absolute value. And the function obviously grows in the northeast direction. And immediately I conclude that the optimal point is A star. Okay, any questions?
So we got all the points approximately or just exactly by the calculation. All the points we get and the is approximately or exactly or certainly.
Exactly. We have found the optimum point A. So I have no approximations. I understand from my sketch. Once again, geometry is the art of good reasoning using bad plot. So my plot is not exact; it's approximate plot. But thanks to a brave guy who spotted my mistake, my plot is qualitatively correct. So line number 1 intersects line number 3 above intersection of 1 and 2. Okay, so my plot is qualitatively correct. That's important. And the location of point A is calculated exactly. So the optimal point A is the intersection of line 1 and line 2, yeah, and it's calculated exactly, yeah. The calculations. So I'm not just measuring the distance. I'm not taking like a ruler and I'm not measuring the distance. I'm solving the equation. But to understand which equation to solve, I use the sketch. So basically, I'm not just measuring distance on the plot. That would be very approximate. I'm just using plot qualitatively, and that's okay. Okay, so A star, yeah.
Boris Borisovich, the answer would actually depend on the slope of the function that we try to maximize.
Yeah, obviously.
So if it was flatter than the line,
with another slope, we may get. So obviously, we should pay attention to kinks of our quadrilateral.
Yes.
So we should pay also attention to that point or to that point. Yeah. When we live in a linear world, then a small change of slope and the optimum will be in B, or maybe the whole segment from A to B may be the optimal set. Do not forget that the optimum may not be unique. So in that case, you may have a whole segment from A to B as an answer.
Mm-hmm.
Okay, so if the slope was not -7/8 and it was -1/2, then the whole segment from A to B is optimal. And if the slope is something like -1/1,000,000, then only the point B is optimal. You're right that the slope of the goal function is important. Okay, we go on.
Let's go.
Okay, basically, we have solved Dual problem, not the original one, but dual, but we have solved. So let's summarize the solution of the dual problem. We are half on the way to the solution of the original problem. So what is summary? Summary. That one is 3 and 1 over 3. That 2 is 3 and 1 over 3. Which inequalities are active or non-active? Summary of the dual problem solution. These are optimal points. The first inequality is active. Why it's active? Just look at the plot. At the point A star, the first inequality is active because the point A star exactly lies on the corresponding line. Is the second inequality active?
No. Second, yes. Second, yes.
Yes. And the third one?
No.
No.
And the fourth one?
No.
No.
First
Okay.
one.
And it's active, not active, not active. Now let's go to dual problem, because dual of dual is our original problem. If we go from dual problem to that, we will obtain our original problem. So what is the correspondence between original problem and dual problem? Lambdas in the original problem are variables in the dual. Lambdas in the dual are variables in the original. So this is, what is Z1? Is a Lagrange multiplier. So what is the role of Z1? Z1 is a Lagrange multiplier for which inequality? For first inequality, for that inequality. 2x1 plus 1x2 plus 1x3 plus 5x4 is greater than 7. So it's a Lagrangian multiplier that corresponds to 2x1 plus x1 plus x2 plus, I forgot, 5x4 less than 7, yeah, I forgot. No, greater than 5, 6. Let me copy. 5, 7, 6, 5, 6, 7, 8. Yeah, like that. And x1, z1 is a Lagrange multiplier for the second inequality. x1 plus 2x2 plus x3 plus 6x4 greater than 8. This inequality that is active, that was the inequality that 2z1 plus z2 is less than 10. The corresponding Lagrange multiplier is the original variable. The original variable is x1. The second inequality was z1 plus 2z2 is less than 10, and the corresponding Lagrange multiplier is x2. So the z1 plus z2 was less than 7, and the corresponding Lagrange multiplier is x3. And the x4 is a Lagrangian multiplier that corresponds to the inequality 5z1 plus 6z2 is less than 100. This is the correspondence. Once again, variables in the original problems are just Lagrange multipliers in the dual problems. That's basically the only correspondence we have between these two problems, but it's very powerful. Okay, what can we conclude? if Lagrange multiplier is positive, what is the conclusion about the inequality? If lambda is positive, then inequality is active, non-active?
Active.
Yeah, is active. Basically, we have a rule that lambda times dl d lambda is 0. So that's the main rule, the main correspondence rule. And if lambda is positive, then instead of inequality, we should have equality. And the second rule, if inequality is not active, then lambda is
0.
Is 0. Because you should have at least term that is equal to 0 in this product. The product should be 0. If lambda is not 0, the second term should be 0. If the second term is not active means not 0, then lambda is 0. Okay, so basically using this correspondence rule, this is correspondence rule in one formula, and that is the same rule in 2 sentences. Okay, if I have these 2 sentences, then what I can conclude? I can conclude that this number is positive. So this inequality should be
Equality.
Yeah, should be active. The second Lagrange multiplier is positive. So the corresponding inequality should be active. This one is not active. So x3, the Lagrange multiplier, should be 0. The fourth inequality is not active. The corresponding Lagrange multiplier should be 0. I can conclude nothing from active inequality. If inequality is active, it may happen that the corresponding Lagrange multiplier is positive. It may happen that the corresponding Lagrange multiplier is 0. I don't know. Basically, here I don't know what happened.
Excuse me.
Yeah.
Am I right that we plug in that 1 equal to 3 and 1/3 to our inequalities, and we check if it is less or equal to 10, then it is okay. But if it is bigger, then it's not okay. Or just what?
Active means equality. Not active means satisfied, okay, but satisfied as inequality. So if you plug in 3 and 1/3 into this inequality, it's true. Yeah, the statement is true. 3 and 1/3 plus 3 and 1/3 is less than 7. That's okay. The inequality is satisfied by its, but it's not active. Not active means true, but inequality. Active means true, but equality. And you may have.
How did we get that it is not active?
What?
We just take the derivative.
Yeah, you may plug in. Yeah, you may plug in, but I draw my conclusion from the picture. In a complex case, obviously, you can just plug in values into inequalities, but in my case, just look at the picture.
Okay, can you return, please? And
The maximum.
explain why it's not, because it is above our point.
Yeah.
I see a point. Okay, thank you.
Yeah, A belongs to the line 1. Yeah, A belongs to the line 1. A belongs to the line 2. A does not belong to the line 3. And A does not belong to the line 4. So I concluded graphically. But you are right that if you are not sure, maybe a line is very close on the plot, and you are not sure, then in that case, to check whether the inequality is active or not, you just plug in numbers and you check whether you have an exact equality or it's not equal. Okay. Okay, I assume that we can go on, but if you have
we
any...
can go. Let's go.
So, what is my logic to go back to the original problem? That one is positive, so I can conclude to 2x1 plus x2 plus x3 plus 5x4 is 7. Z2 is greater than 0, so I conclude that x1 plus 2x2 plus x3 plus 6x4 is 8. Number 3 is not active. I conclude that x3 is 0. Number 4 is not active. X4 is 0. Bingo. I have almost solved the original problem. Yeah. Now, 2x1 plus x2 plus 0 is equal to 7. x1 plus 2x2 plus 0 is equal to 8. x3 is 0, x4 is 0. Bingo! I multiply by 2. I will have 4x1 plus 2x2 is 14. x1 plus 2x2 is 8. I subtract. I get 3x1 is equal to 6. x1 is 2.
Minus 3x1.
Why?
Oh, not. Oh, yeah, I did a mistake. Sorry.
Yeah, I may do mistakes, so be careful. That's right to be. That's perfect that you try to solve it by yourself. That's very good. Try to solve by yourself, and if you think that I have made some arithmetic mistakes, that's okay, because it's my big problem. I'd like to improvise, and with online teaching, that's very hard, because on the whiteboard I leave my previous writings on the big whiteboard, and if I spot a mistake, I can easily spot it after 5 minutes, because I can see what I have written. And in that case, the screen will disappear in 5 minutes, because there are not enough place, and it's a little bit tricky to spot a mistake that in the past. So be brave, and I always appreciate your efforts when you say that you have spotted a mistake. So thank you for being attentive. Okay, I think x2 will be 3. Yeah, like that. 4 plus 3 is 7. 2 plus 6 as 8. Yeah, that's great. Woohoo! x1 is 2. x2 is 3. x3 is 0. x4 is 0. Yoo-hoo! We have solved without Lagrange multiplier, without explicitly writing Lagrangian function. Yeah, we have used theory of Lagrangian function, but we have not done first order conditions explicitly with all inequalities. So we have solved problems. We have used implicitly, we have used this rule. Yeah, so we need Lagrange theory to solve the problem, but the solution was graphical. We have solved the dual problem, and we have gone back to the original one. Any questions?
No questions. Thank you.
Okay, a small miracle. Just let us look. Small miracle. Small miracle. duality strikes back. Yeah, let's calculate the value of minimum and the value of maximum. What is the minimum of the original problem? What is the minimum? Oh, I forgot the numbers. Sorry. 10x1 plus 10x2 plus 7 plus 100. 10x1 plus 10x2 plus 7 plus 100. And it is 10 times 2 plus 10 times 3, it's 50. Okay. And what was the maximum of the dual problem? That is 7z1 plus 8z2. Oh, it's 7z1 plus 8z2. It is 7 plus 8 times 3 and 1 over 3. It's 15 times 3 and 1 over 3. It's 45 plus 5. It's 50. Wow. Not only the variables of the original problem, the Lagrange multipliers of the dual problem, but the extrema are equal. So we have one more link between original problem and dual problem. One more link. The minimum of origin, so extremum values of dual problems are equal. So if the goal on the exam, for example, or in some machine learning tests is just to find the value of extremum, then we need to solve only the dual. We even don't need to go back to the original problem. Oh, it's windy outside. Okay, let's go on. What should I? So one more link between dual problems. So let us provide intuition to this link because it's not too hard. So let's interpret these two problems and let's understand why it's more or less obvious that we have a link like that. Okay, so I will try to convey the, so we have proven that first order conditions are equal using Lagrange multiplier theory, but I would like to provide economic intuition to better understand without equations at all why these problems are linked and why the result, the optimal value, is the same in both problems. So once again, I will consider these two problems. So the last topic I would cover is economic interpretation of duality. Once again, let's consider original and dual problem. Problem A was to minimize 10x1 plus 10x2 plus 7x3 plus 100x4, given that everything is positive, oh sorry, not negative, and I don't remember once again the constraint, but if I'm not mistaken, it was something like 2x1 plus x2 plus x3 plus 5x4 is greater than
7.
Thank you. x1 plus 2x2 plus x3 plus 6x4 is greater than 8. And the dual, I will write it in red. The dual problem was maximize 7z1 plus 8z2. That one is greater than 0, z2 is greater than 0, subject to. And I have 4 inequalities here. 2z1 plus z2 is less than 10, z1 plus 2z2 is less than 10, z1 plus z2 is less than 7, 5z1 plus 6z2 is less than 100. So my goal now is to convince you without first order conditions that it was more or less obvious that the optimal values are the same. More or less, we have proven that last week because the Lagrangian function is exactly the same. So if you plug in the same values in exactly the same Lagrangian function, you would obtain exactly the same value. But why it's more or less obvious from interpretation? Let's interpret something like that. Or I will, so imagine that Robinson-Crusoe produces what he will produces like what he will produce guns and flowers. So imagine that Robinson Crusoe, he produces guns. So Z1 is a number of guns. So this is number production of guns. And Z2 is a production of flowers. And these are the prices. So 7 is the price of one gun, and 8 is the price of one flower. Okay, so this is a problem we can interpret as Robinson Crusoe maximizes his revenue 7 times the number of guns produced plus 8 times the number of flowers produced. And these are some resources. For example, he needs, so this is amount of, so this is like he has 10 hours per day of labor. So this is labor restriction. So this is like, I don't know, land restriction. That is, I don't know, water restriction. He has 7 units of water, and to produce one gun, he needs 1 liter of water. To plant one flower, he needs 1 liter of water. So he has 7 liters of water. So number of guns produced plus number of flowers produced is less than 7. And that is, I don't know what it is. 5 that one. Well, he needs 5 what?
Air.
Instruments.
Air instrument.
Positive
yeah.
attitude.
Yeah, the restriction smiles. These are smiles. He uses 5 smiles to make a gun and 6 smiles to make a flower. Okay. And every day he has 100 smiles, and he spends these 100 smiles. He on the production of guns and production of flowers. Okay, so basically, what's the interpretation of problem B? Problem B, he maximizes his total revenue by using as possible his everyday resources. Every day he has 10 hours of labor. Every day he can use 10 square meters of land. Every day he can use 7 liters of water. And every day he can use 100 smiles. Okay? So the problem B is clear, the interpretation. Okay?
So in the B, he maximizes the production, and then in A,
not
he
production, total
minimizes.
revenue. Seven is the price of one gun, so it's a total
Oh,
revenue.
total revenue. Okay.
Total revenue. Because he sells every gun for 7 rubles, every flower for 8 rubles. Okay. This economy is very specific. Yeah. In this economy, he is not. So we may imagine this economy that unused resources like unused minutes, it depends on your operator mobile, but for some mobile operators, if you have unused minutes or unused megabytes, they just burned. Yeah. And in this example, unused resources are burned. Yeah. If one restriction is more restrictive than the other, yeah, we know that these two restrictions are actually active, and these two restrictions in the solution of the problem are not active. So every day he has more water than he can use, but in our case, he cannot just take this water and use it another day. So unused resources are burned in this model. Yeah, and let's go and let's interpret the problem A. What is the interpretation of problem A? Imagine that Robinson Crusoe now he doesn't like to be entrepreneur, and he just likes to be likes to work for some person. And now Robinson Crusoe just say he arrives and says, "I'm ready to work for you. Every day I can work 10 hours. That's my labor. I can use my land, 10 square meters. I have every day the supply of 7 liters of water, and every day I have 100 smiles. What I can do for you? How much would you pay me?" And let's imagine a problem of hiring Robinson Crusoe. So that's a problem of hiring. I would like to hire Robinson Crusoe. As I would like to hire Robinson Crusoe, I would like to pay him as less as possible. But I would like I would like that he agrees to my proposal, but I would like to pay him as less as possible. So that will be the wage of Robinson Crusoe. I say, for every unit of labor, I will pay you X1. So if you use 1 hour of labor, I will pay you X1. For every unit of land, I will pay you X2. For every liter of water you use, I will pay you 7. For every smile, I will pay you X4. And let us look now that the problem A, I minimize my total spending on Robinson Crusoe. And these two equations, these are agreement equation. These are agreement inequalities for Robinson Crusoe. When Robinson Crusoe will agree my proposal, when my proposal is better for him, then he can do without me. What he can do without me? Just be careful. If he likes to produce one gun, he needs to use 2 units of labor, 1 unit of land, 1 liter of water, and 5 smiles are enough to produce 1 gun. And for 2 units of labor, for 1 unit of land, for 1 liter of water, and for 5 smiles, I pay him exactly 2x1, 1x2, 1x3, and 5x4. And so basically, he will agree if he receives from me not less than 7, because using the same resources, he can produce 1 gun and sell it for 7 rubles. So the first one is that the condition basically says that resources used for production of 1 gun should give Robinson Crusoe not less than 7 rubles. Okay, if he sells his resources, then he should receive not less than the price of a gun. And the second inequality, the meaning is just the same. What Robinson Crusoe receives for resources used to production of 1 flower should be not less than the price of 1 flower. Otherwise, he will not agree to my proposal. And basically, I minimize the price I pay for his resources, provided he agrees. And basically, A and B from economical viewpoint may be interpreted as a firm valuation from inside of the firm, the problem B. We maximize the total revenue. And the problem A is I like to buy the firm all the resources of the firm. I have one condition that the owner should agree to sell the resources, and I'd like to pay the minimal possible price. Okay?
Okay.
And so basically, that's the price of the technology plus resources. The price is the same, technology plus resources, so maximum is exactly the minimum. And so it's economic interpretation of duality, and that's why X1 is it's called a shadow price of labor in our case. Yeah.
Excuse me, how do we use such kind of technologies in real life, like to make
Sorry?
the company? I don't know how to make such kind of technologies works in real life. Is there any examples?
Linear programming in real. So if your question is how it's applied in real life, many problems they are too complex to solve. Many problems are too complex to be solved, and very often linear approximations are constructed, linear approximations are solved, and then that's how many trading strategies are optimizing with, I don't know, 100,000 parameters in linear programming problem, and that's how many trading strategies are organized. Or when I don't know, the form of a new airplane is calculated, linear programming problems is solved. So linear programming is widely used. Yeah, in this example, obviously, a toy example, one never buys or sells a firm using such simple models. Yeah, you are right. My idea was just to explain why that's not just coincidence that the maximum value of original problem was the minimal value of the dual. My idea was to show you that we have reasons behind this fact. But obviously, this is a toy problem. And in real life, when linear programming is applied, the number of variables is very big. For real life problems, when it's applied, the number of variables is 1,000, 100,000, 1 million. So real life problems are approximated by linear programming problems.
Thank you.
Okay, X1 is shadow price of labor. And what does it mean that the price X3 is 0? The shadow price is 0 when? When the resource is not, we have too much of the resource. So for example, we have 100 smiles, and so the smiles, they cost nothing. X4 is 0 because the corresponding inequality is not active. So we smile for free. The good conclusion of the lecture. So what we have done today, we have considered an example how to go from a problem to a dual. Sometimes it's very useful when we have 4 variables and 2 constraints. You go to dual, you have 2 variables, you draw. When you draw, you can solve it graphically. Solve it graphically. Oops, you have the solution basically very fast. You obtain when you can use graphical approach, and the solution is easily obtained. Okay, see you next time. That's all for today. Have a great evening.
See you.
Thank you.
Smile more.
Weekend. Bye-bye, Boris. Love you.
Thank you very much. Have a nice weekend.
Bye.
Bye-bye.